Hello, and welcome to section 6.6, halfway through chapter 6 here. And we're going to talk a little bit about how to read energy diagrams a little more specifically, because there are some nuances here that we should talk about. So remember, we talked before about how if you have, we'll just say potential energy instead of Gibbs energy, and that goes up as you go up the y-axis, and the reaction progress that goes forward as you go up right on the x-axis. Then you have some reactants, some products, potentially, some activation energy that gets you to the product. But what if you have the case where you could make two different products? Okay, so what does that mean? So instead of this very simple example, what if we have reactants here, and they can go to product one here, or product two. Oh, sorry, this should be farther down. I made this a little small. Nope, product one is here. We'll say product one is there. And product two is here. So both are still less energy than R. So that means it should be exergonic and spontaneous. But now let's do blue. The activation energy for the blue one is higher than the activation energy for the second one. So now we have a conundrum here, right? Because thermodynamics would tell us that P1 is actually the favored product. So let's write this out here. So thermo, that is Gibbs free energy, tells us P1 is favored. Because the delta G is more negative than for P2. But kinetics tells us that P2 is favored because the activation energy is lower. So what do we do here? How do we know what molecule or what product will come out of this reaction? And the answer is it depends on the temperature. Because here the activation energies of both are set, right? Here and here. The energies of the products are set. We don't know the sterics of the reaction. So the only thing that can change is the temperature. Remember, the temperature is kind of like the baseline energy here. So if we were to, let's say, we're going to make temperature, we're going to put temperature in red here. If the temperature were really high and there was so much energy that the system could come into full equilibrium and choose the most beneficial negative delta G value, if the temp is high, then P1 will be favored because of the thermodynamic equilibrium that we reach. So in this case, we would call P1 the thermodynamic product, which is short for thermodynamically favored product. Let's make this font bigger here. There we are. Okay, so that's one scenario. But let's change the color on our temperature here. Let's say it's in green now. So if temperature were low, and it's around here somewhere, right? If temperature were low, then there's less activation energy there's less energy that can be used for the larger activation energy to make P1, which means that the molecule really only has enough energy to get over that lower energy barrier for P2. So because that's the case, temperature low, P2 is favored in this specific example, which means that P2 would be called the kinetic product because the P2 product would be kinetically favored because, remember, kinetics deals with the rate and not the equilibrium. And the rate of formation of P2 will be much faster than P1 because the activation energy is much lower. And your book goes over some other examples that are a little easier to read, such as if you have this type of energy diagram where potential energy is increasing on the y-axis and reaction is increasing along the x-axis. If you have some reaction that happens here and two potential products, P1 and P2, but essentially P2's activation energy is too high and the energy level for P2 is too high, then P1 is favored in both cases. All right, so then the last thing we'll talk about here in this chapter is another thing that happens. Instead of a one-step reaction, you can have more than, or it's not the last thing we're talking about, but it's almost the last thing. Instead of one-step reaction, you can have multiple step reactions that you display using energy diagrams. So here, again, potential energy increases going up the y-axis, and it decreases, or sorry, the reaction increases going right on the x-axis. You can have a case where your reactant here makes a product that's lower in energy, but along the way, in order to make this happen, you come into some intermediate structures. And each of these intermediate structures has its own activation energy that it has to go through. Like this. And the tops of these mountains that we just made are called transition states. And they're so called that because they represent the transition between the reactant and product, or reactant intermediate, or intermediate and intermediate, or intermediate and product, whatever it is that you're talking about. Transition state. You can think of them as the hills and the intermediates as the valleys. Now, the transition state is also important because it represents the exact final resting place of a molecule before it forms whatever it's going to form. Because when you reach the top of this mountain, it never stays there. It either goes backwards or it goes forwards. Either way, but you can't just stay on top. So how this really comes about, or what this really, how it's really useful, is that let's say you had some reaction, like an acid-base reaction, right? Let's do this in purple. So you have some base, like a nitrogen. There we are. Okay, this is just ammonia. And you're going to react that ammonia with, let's say, methanol. Okay, we already talked about before in the acid-base chemistry chapter how the mechanism for this starts at the lone pairs. The hydrogen is attacked, and then those electrons from the methanol oxygen go back and reside on the oxygen itself. So this is a reaction where electrons are moving. And if you could display this reaction using a potential energy diagram, you would see the reactants here, some activation energy to make a transition state that eventually ends in a product, right? Well, the transition state represents an actual chemical structure that's formed. And here you could imagine that even though the reactant or the reaction occurs to give you the two molecules here, these two, that there should be some intermediate structure that we're talking about, right? Because the electrons are physically taking this proton. So the transition state, called TS, sometimes TS double dagger, represents the case where the nitrogen, the bond distance between the nitrogen and the hydrogen it's taking is about equally distant from the nitrogen, or sorry, the hydrogen in the middle is equally distant from the nitrogen and the oxygen that it was on before. And so the transition state, the physical translation of the transition state is that if the hydrogen moves even 1 nanometer, picometer even, in one way or the other, then the nitrogen or oxygen take ownership of that proton. But right now it is in the exact middle, and any little bit of energy could push it one way or the other. So this is what is meant by a transition state. And if you notice, these two molecules I'm showing having they have the H equally. However, something called the Hammond postulate, which is a key thing in reaction theory, the Hammond postulate says that the transition state resembles the molecule that is closest in energy to it. So that means if you have some reaction where potential energy is going up on the y-axis and the reaction progress is going forward towards the right, if you have a case where the reactant is closer to the transition state than the product, like this, see there's less distance between the reactants than with the products, then the transition state looks more like the reactant than the product does. Your book has a nice little example of that in page 243 in figure 6.22. Okay, so I think that is probably where we'll stop here in section 6.6. Hopefully you found this useful.